So for today, we'll be doing section 3.5 of our course. This is cross product. And this cross product is actually another operator on vectors. But to be more precise, we only operate on vectors in the tree space. So this cross product only applies to vectors on tree space. Okay? So how do we define this cross product? Let's start with the definition here. So let us get two vectors in tree space. Say vector u with components u1, u2, and u3, and vector v with components v1, v2, and v3. Okay. Then the cross product of u and v, which we denote by u cross v. Okay, this is read as u cross v. This is the vector defined by the following. So u cross v is the vector whose first component is equal to u2 times v3 minus u3 times v2. Okay. The second component is u3 times v1 minus u1 times v3. And the third component is u1 times v2 minus u2 times v1. Okay. So I know this definition here may be difficult to memorize. So what we're going to do is to write this equality here, okay, or write this part here in an easier format, okay. So this u cross v is just the determinant of this 3 by 3 matrix. So in the first row, you just have I, J, K. So remember I, J, and K, these are the standard unit vectors in the tree space, okay? On the second row, you have the components of U, okay? The components of the first factor. So our first factor here, it's U. So you have that U1, U2, and U3. And on the last row, okay, they are the components of the second factor V. So the last row is V1, V2, V3. So if you calculate this determinant, you will obtain this guy here. Okay? You will obtain this guy here. So on the first component, you just have U2, the determinant of U2, U3, V2, V3. On the second component here, you have minus U1, U3, V1, V3. While on the third component here, you just have U1, U2, V1, V2. Okay? So, to easily remember this, look at the determinants in the first component. You are removing the first components of U and V. You get the determinant of the matrix without the first components there. Okay, so that's your first component for the U cross V. For the second component, you actually remove the second components for U and V. So you have U1, V1, U2, V3, U3, V3. But don't forget the negative. Okay, and then for the third component of U cross V, you remove the third components of U and V. You now compute for the determinant of U1, U2, V1, V2. Okay? So if you still don't, or you still can't memorize this, you can always go back to this determinant here. Just remember, you have I, J, K in the first row. On the second row, you have the components of the first factor. And on the third row, you have the components of the third factor. And again, noting that I, J, and K here are the standard unit vectors in the tree space. Okay? So if you do this part here, what you will get is the following. So this guy here, it's equal to the quantity U2, V3. So look at this. So I times the determinant of this guy here. Okay, U2 V3 minus U3 V2, and then there's your I there. Okay, plus you have the negative 1 raised to 2 plus 1, or 1 plus 2. Remember the cofactor expansion. So negative 1 raised to 1 plus 2, and then you have your j, right? So in essence, we are calculating the determinant using the cofactor expansion along the first row. Okay? So you now have this. So you have the determinant U1 V3, U1 V3 minus U3 V1, U3 V1. And then plus the other guy here, you have negative 1 raised to 1 plus 3, which is positive 1. So I'm not gonna write that guy there. So plus quantity, you have your k here. And then for the k part, so you are now looking at this. So you just have this submatrix here. So U1 V2 minus U2 V1. So that's this vector here. Okay, and easily you can compare this guy here to be this guy in this definition. Here you have negative 1 because you have the exponent 1 plus 3, which is an odd number. So you have that minus here. Okay, in here you don't see that because you already interchange, or we already interchanged the location of the two guys here. Okay, and then the last component, you have this guy here. Okay, so that's the cross product of two vectors in the tree space. Okay, now please be careful when doing the cross product. I'm telling you now that the location of the factors u and v, they are important. Later you will see that when you interchange the two, something will happen. Okay, something will happen. So remember that if you have the first factor u, the components of that first factor u must be on the second row in this notation. And then the components of the second factor, say your second factor is the vector v, the components must be on the third row. Okay, so do not just interchange these two components, set of components. So for example, let's have u and v here, and then let us calculate the cross product u cross v. So again, let us use that determinant notation. So you have u cross v. This is the determinant I, j, k. And then you have 1, 3, negative 2. And then negative 5, 0, 3. Okay? So you can do the cofactor expansion from here. Okay, you can do the cofactor expansion. So you have your negative 1 raised to 1 plus 1. Okay, which is positive 1. So I'll not write that. Then you have your I. Okay, you have your I here. And then the determinant of the submatrix obtained by removing the first column, first row, and first column. So you will have 3, negative 2, and then 0, positive 3. Okay? And then for the j, you have negative 1 raised to 1 plus 2. So let's just put minus. And then you have the determinant of something, and then you have your vector j here. And this is your j. You remove the second column and the first row. So you will be left with 1, -2, or you will be using the submatrix 1, -2, -5, +3, and then plus, again, -1 raised to 1 plus 3, which is +1. So I'll not gonna write that factor -1 raised to 1 plus 3. And then determinant of the submatrix, and then your vector k. So for the vector k, you remove the third column first row. So you will have 1, 3, -5, 0. Okay? And then just simplify. So you have here what? 3 times 3, that's 9, and then this is 0. So you will have 9i. And then for this minus, you have 1 times 3. So you have 1 times 3, that's 3, minus -5 times -2, so plus 10. -5 times -2, that's plus 10. So minus 10 in here. And then j, and then plus quantity. For this, you have 1 times 0. So that's just 0. And then you have -5 times 3. That's minus 15. So minus -15. And then you have your k. Okay? And we write this in vector form. So this is just 9, comma. You have 3 minus 10, that's -7, but there's negative in here. So that's +7. And then for this, you have -15, that's +15. So this is the cross product of these two guys here. Okay? For item number 2, let's do the same thing. You have the cross product of UV. So it's the determinant of this matrix, I, J, K. For the second row, you have -2, 0, 6. And then for the third row, you have 1, -3, and then 1. Okay? So work on your desk and let us compare answers. So in here, I will have determinant of 0 times 0 here, 6, -3, 1, and then you have your I. Then minus determinant of -2, 6, 1, 1, and then you have your j, plus determinant of -2, 0, 1, -3. And then you have your k. Okay? And then let's find the determinants here. So you will get, on the first, you have 0 minus -18, I, minus quantity. On the second, you will have -2 times 1, that's -2, minus 1 times 6, that's 6, and j, plus on the third one, we have -2 times -3, that's 6 minus 0. So let's just write 6k. And again, in vector form, this is 18. This is the vector with components 18, 8, and 6. Okay? This is what you get. So question so far for the definition of cross product, we have this. Okay. Now, let us look at some properties of the cross product. Okay. So in here, um, we look at the relationship between the dot product and the cross product. So let U, V, and W be vectors in 3 space. Then we have the following. Okay, U dot quantity of U cross V, this is equal to 0. So look at this. Since you have the parenthesis here and it contains U cross V, you start with this U cross V. Okay, after getting the U cross V, you dot it with the vector U. Take note. Okay, take note. You have to apply dot product on 2 vectors. Okay, you have to apply dot product on 2 vectors. U cross V, it's a vector. So you can do the dot product. Okay, but this first item here tells us what? U dot U cross V is equal to 0. And remember, if you have, if you dot, if you get the dot product of 2 vectors and it's equal to 0, it means that the 2 vectors are perpendicular to each other, or they are orthogonal. And this first item tells us that U cross V is orthogonal to the vector U. Okay? So U cross V is orthogonal to the vector U. Similarly, for number 2, you have vector V, dot it with the U cross V. And it's also equal to 0. And this tells us that U cross V is also orthogonal to the vector V. Okay? So you have the cross product, U cross V. It is orthogonal to both of the factors in your cross product. Okay? Next property here, you get the U cross V, you get the norm squared of that. You can calculate this by doing this right-hand side. Norm of U squared times norm of V squared minus U dot V squared. Okay? So remember, you get norm, it's a number or it's a scalar. Okay? So this guy here, norm squared of V of U times norm squared of V. These are both numbers. So if you multiply them, it's just a number. And dot product, it's a scalar. So it's a number. So this guy here makes sense. U dot V, it's a number. You square it, it's another number. And you can combine them. So this is a number minus another number. It will give you another number. So this equality at least makes sense. Okay? And we call this the Lagrange identity. Okay? So it has a name because it might be helpful in our future computations. Okay? Now, the fourth and the fifth, okay, the fourth and the fifth identities here, we call this the vector triple product. Okay? So in here you see U cross V, U cross V cross W, okay, U cross V cross W. This is equal to the following. U dot W times V, so this is a scalar times the vector V, minus U dot V W. So again, U dot V, it's a scalar, you multiply it to W, it's a vector. Which means what? This guy here, it's a vector. This guy here is also a vector. You combine them, it's also a vector. And that should be the case because you have the cross product of V and W, it's a vector. And then you have to cross that with U. So you cross this vector here. It will give you another vector. Okay? So you have to make sure that at least the identity has the same unit or has the same or in the same object, okay? So vector here, vector on the right hand side. Here you have a scalar on the left hand side, you must have a scalar on the right hand side, okay? So that's your number 4. For number 5, look at this. We changed the grouping. So in here, you start with V cross W, and then you have U cross V cross W. On this guy here, you now start with U cross V before crossing with W. Okay? For this right-hand side, you have U dot W V. So it's the same as this guy here. Okay, on the fourth identity on the right-hand side, okay, the first factor or the first addend, it's this, they are the same. But the second here, they are different now. Okay, so U dot W V minus V dot W U. Okay, V dot W U. Okay, so changing the grouping changes something in your computation. So you have to make sure that you are following the order of your factors. Okay. So these two guys here, 4 and 5, it's just for your information, at least in our case, but we rarely see this in our examples. But it's good to know that we have these two identities here, the vector triple product. Okay. So let's look at this example. So we verify these two identities here, 1 and 2. More precisely, we want to show that U cross V is orthogonal to both U and V. Okay? So we want to show that the cross product U cross V is orthogonal to both U and V. Okay? So these are the items, or these are the vectors that we are going to use. Okay? And these vectors here, these examples here, we actually did the cross product already. So let's just copy the cross product there. So for the first set of vectors here, we have 9, 7, 15. So 9, 7, 15. So U cross V, this is 9, 7, 15. And then for the second vector here, U cross V, we have 18, 8, 6. 18, 8, 6. Okay? 18, 8, 6. 18, 8, 6. Okay? So we have the cross products. Okay? We will show that if we cross U with this, or if we cross V with this, we'll just get 0. Okay? If we if we dot U cross V with U or with V, okay, we should get the 0 scalar. Okay? If we don't get that 0, it means something is wrong with our computation. Okay? So let's see, let's start with that. So we want to dot U with U cross V. So our U, it's 1, 3, negative 2. Dot it with the U cross V, 9, 7, 15. So for the dot product, we just multiply the component wise. So 1 times 9, that's just 9. 3 times 7, that's 21. So 9 plus 21. And then minus 2 times 15, that's negative 30. So minus 30. And indeed, 9 plus 21, that's 30. Minus 30, this is equal to 0. Okay? For the other guy, you have V dot U cross B. U cross B. So our vector V, it's negative 503. So negative 503 dot it with the other guy, which is 9, 7, 15. Let me adjust this. Okay. So you have 9, 7, 15. So what do we get? Negative 5 times 9, that's negative 45. And then you have 0 times 7, that's 0. And then 3 times 15, yeah, that's 45. So this is equal to 0. Okay? So at least for this example, we have shown that U cross V is orthogonal to both U and V. Let's use this example and show that it's also the case. So you have U dot U cross V. You have negative 2, 0, 6. This is dot with 18, 8, and then 6. So this is equal to negative 2 times 18. That's negative 36. Then you have 0. And then you have 6 times 6. That's plus 36. So indeed, this is equal to 0. And then for the other guy, you have V dot U cross V. And our V, it's 1, negative 3, 1. Then dot it with 18, 8, 6. And then here you will get 1 times 18, that's 18. Negative 3 times 8, that's negative 24. And then 1 times 6, that's 6. Yes, 18 plus 6, that's 24. So minus 24, that's equal to 0. Okay? So we have verified the property in this set of vectors. Okay? So basically, one implication is that we did the cross product correctly. Okay? We did the cross product correctly. Okay? Question? Now, more properties. Okay? So, let U, V, and W be vectors in 3 space, and let K be any scalar. Okay? Then, so you have the cross product U cross V. It's equal to the negative of V cross U. Okay? So if you interchange the factors U and V, you have to take out a negative. Okay? And this identity here, you can easily see that in the determinant form of the cross product in here. Why? Because as we have said, the first factor in the cross product will be the second row. The second factor will be the third row. If you interchange them, then you will also interchange this. Meaning this V1, V2, V3 will be on the second factor, in the second row, and U1, U2, U3 will be on the third row. But remember, if you interchange two rows, okay, if you interchange two rows, when you are trying to compute the determinant, you have to take out a negative. Okay? When you interchange two rows and you are computing determinants, you have to take out a negative. So that's why you have to be mindful in the order of the factors in the cross product. Okay? So take note of that. U cross V is equal to negative V cross U. For the second here, we have the distributive property. So U cross V plus W, it's equal to U cross V plus U cross W. And take note, U is on the left factor. Okay, U is on the left factor here. So when you distribute it, your U must remain on the left factor. Okay, so U cross V, U cross W. Now here, still distributive property, U plus V cross W. This is equal to U cross W plus V cross W. So in this guy here, W is on the right factor, okay, of this cross product here. So your W must remain on the right factor. So U cross W plus V cross W. So don't interchange them. It's very different with the dot product or just the usual multiplication. Okay? This tells us that the cross product is not commutative. You can just interchange them. Okay? Question so far. For the fourth identity here, scalar k times u cross v. Okay? It's the same as ku cross v, which is also equal to u cross kv. So the scalar k, you can attach it to any of the factors, and you will still get the same answers. Okay? So here, your k, it's attached to the cross product u cross v. In here, your k, you multiply it first to u. And then in here, your k is multiplied to v first. Okay? So that scalar can move freely. But make sure, again, the location, u cross v. So you still have here, u is on the left factor, v is on the right factor. Here, you have the same. Okay? Number 5. Of course, if you cross any vector with a zero vector, you'll just get the zero vector. Okay? This is trivial. Number 6, you have the cross product of u with itself. You will get the zero vector. Okay, and this guy here can easily be seen if you work on the determinant form. Because of course, your second row will be the components of u. The third row will also be the components of u. So if you have proportional rows, remember, your determinant is equal to 0. Okay, but this guy here tells you that you are actually, you have the same row, or you have the same entries in rows 2 and 3. So automatic, it's 0. Okay, question so far. Okay, so let's look at, let us use this cross product geometrically. Okay, or let us apply this cross product in Euclidean geometry. Or yeah, anyway, so let us look at a parallelogram determined by two vectors, and let us try to find the area of this parallelogram. Okay, so what is this? For example, this is your vector u, and this is your vector v. Okay, this is your vector v. So let me put the arrowheads here. So you have two vectors with the same initial point. Okay, you can generate a parallelogram with u and v as adjacent sides. So if we construct the parallelogram, this will be something like this. So this is that, this is that. So you will have this parallelogram here, okay? And our goal is to find the area of this parallelogram. Okay? So how do we calculate this area? Okay? Let's look at this. Remember, if you have a parallelogram, the area of the parallelogram is equal to area of the base, or the length of the base times the corresponding height. Okay? So if recall from your Euclidean geometry that if you have some parallelogram, something like this, you just get the height here, and then you have the base here, okay? And the area will be equal to base times height, okay? So what we're going to do is to look at the height of this parallelogram, okay? And then get the height and get the length of the vector, okay? Vector where the associated base, okay? So you have the height. Suppose this is the height that we want to get, okay? Suppose this is the height that we are going to use. The associated base will be this guy here, the vector u, okay? If you want to use your vector v as your base, then your height must be towards that direction. So this will be your height. Okay, this will be your height if you want to use this vector v as your base. Okay, so looking at this, you have two possible bases, this guy here and this guy here, but you are using this as your height. Okay, you are using this as your height, and therefore the associated base will be this guy here. So it's the same thing. So try to recall that concept from your Euclidean geometry course. But anyway, you have this h, and you have the vector u. We are left to find the value of h here. Okay, we are left to find the value of h here. But the question is, how do we get the value of h? We can start by setting this angle theta. And then notice you will have a right triangle in here. So if you remember from your trigonometry class, you have your SOHCAHTOA. We can use that, okay, to find this height h. So we will need, so this is equal, this tells us that sine of the angle, this is equal to opposite side over the hypotenuse. This is our angle. The opposite side, it's your h. It's your small h here. And then the hypotenuse, it's the length of the vector v. Okay? Which means what? you have from here your h, small h, this is equal to the norm of the vector v, that's the length of this hypotenuse here, times sine theta. Okay? So, the area of the triangle, the area of, area of the parallelogram, the area of the parallelogram, this is equal to, according to this, base times height. So you will have norm of u, okay? Norm of u times h, but your h, it's the norm of u times norm of v sine theta. I mean, the h, it's norm of v sine theta, so that the area is norm of u times norm of v sine theta. So let me just put those vector arrows there. Okay? Now, you might ask, how is this related to the cross product? And we have been talking about the cross product. Okay, look at this. Let us go back to that Lagrange identity that we know here. U cross V squared, the norm of U cross V squared, it's equal to U cross, U, norm of U squared times norm of V squared minus U dot V squared. Okay? So, using, okay, using Lagrange identity, so Lagrange identity, you have the norm of U cross V squared. This is norm of U squared, norm of V squared minus U dot V squared. Now, do you still remember what U dot V is in terms of the angle? By definition, the dot product of U and V is what? So this guy here, it's now equal to the norm of U squared, norm of V squared, minus. By definition, the dot product, it's just U cross, or norm of U, and then norm of V, and then you have cosine theta. Correct? And then you have to square this. Remember that product? We call this sometimes the physicist definition of that product. So U dot V, it's called that it's equal to norm of U, norm of V cosine theta. Okay? It's not official, but we just call it the physicist definition of U dot product. It's not official. It's just we're just making fun of them. But anyway, here you have what? You have the square in here, so you can square this guy. You will get norm of U squared, norm of V squared, and then minus. You have here norm of U squared, norm of V squared, and then you have your cosine squared theta. And then you can factor out norm of U squared, norm of V squared. It's a common factor. So that you will be left with norm of U squared, norm of V squared quantity, 1 minus cosine squared theta. Following? Okay? But what is 1 minus cosine squared theta? That's your sine squared theta. So this guy here, you will have norm of u squared, norm of v squared, sine squared theta. Oops, I forgot the squared in here. Yeah. So what does this mean? The cross product u cross v, you get the norm and you square that, it gives you norm of u squared, norm of v squared, sine squared theta. Which means this tells us that the norm of u cross v, so you have this and you have this, you just take the square root of both sides. Okay, you just take the square roots of both sides. So taking the square root, you'll just have u, norm of u times norm of v times sine theta. But this is precisely the area according to this. So this is equal to the area of rectangle generated by u and v. Okay? So it means you have two vectors, u cross v. You draw the rectangle with sides u and v. If you want to get the area of that, okay, however they are positioned, all you have to do is to get the cross product and the norm. Okay? So that is our theorem here. If u and v are vectors in tree space, then the norm of u cross v, it's equal to the area of the parallelogram determined by u and v. Okay? Let's look at this example. Find the area of the triangle determined by the points P1, P2, and P3. Take note that triangle, it's just the half of the parallelogram. Okay? Triangle, it's just half of the parallelogram. So the area of the triangle is just half of the area of the parallelogram. So you have the 3 points here. Okay? You can get 1 point to be the common, okay, to be the common initial point, and then the vectors will be from that common initial point to the other 2 points. So maybe if this is your point P1 and this is your point P2 and this is your point P3, of course you will be able to form your triangle, okay? But you can have this vector and then this vector. And then if you look at the parallelogram, okay? If you look at the parallelogram, you can use this formula. But this parallelogram is twice this triangle here, the one that we want. So if you want to get the area of the triangle, you just get the area of the parallelogram obtained and then divide it by 2. So this formula here can be used. Okay? So let's use P1 as our common initial point. So we get P1, P2. That's your first vector. Okay? P1, P2. So you have -1 minus 1, comma. So -1 minus 1, 1 minus 2, 1 minus 2, comma, and then 2 minus 0, 2 minus 0. We simplify this. We have negative 2, comma, 1 minus 2, that's negative 1. And then you have 2 minus 0, that's 2. And then you have now P1, P3. Okay. This is your P3, so you have 0 minus 1, comma, 4 minus 2, comma, 3 minus 0. So this is what? Negative 1, comma, 2, comma, 3. So this is your first step. Second step, you get the cross product. P1, P2 cross with P1, P3. Okay, so this is the determinant I, J, K. P1, P2, that's your first factor. So you will have negative 2, negative 1, 2. P1, P3, that's negative 1, 2, 3. So this is equal to, let's do it this way, because anyway, we just started learning this cross product. So I'll do everything, every detail here. So negative 1, 2, 2, 3, I minus determinant negative 2, negative 2, positive 2, and then negative 1, and then 3 here. This is your J plus determinant for this guy, negative 2, negative 1, negative 1, 2. And then you have the K. Okay. Double check if you are copying the correct entries. Okay. Because I can still see in some of you that there are times you are not copying the correct entries. Okay. Anyway, so in here, let's have this guy here, negative 1 times 3, that's negative 3 minus 2 times 2, that's 4. I minus quantity, negative 2 times 3, that's negative 6, minus negative 1 times 2, that's negative 2. So I'll just put plus 2 here. J plus negative 2 times positive 2, that's negative 4, minus negative 1 times negative 1, that's positive 1. And then you have your K. So in here, what is this? Negative 3 minus 4, that's negative 7, I. So let's put this in vector form. So negative 7, comma, negative 6 plus 2, that's negative 4. There's a minus here, so plus 4, comma, minus 4 minus 1, that's minus 5. Okay? Therefore, area of the triangle, it's 1/2 norm of that P1, P2 cross P1, P3. Okay? So we calculate the norm. So this is equal to 1/2 square root of negative 7 quantity squared plus 4 squared plus negative 5 squared. Okay? Okay, so let us see. Is this part here correct? So you have negative 2, negative 1, negative 1, 2. So negative 2, negative 1, negative 1, 2. So you have negative 2 times 2, that's negative 4, minus negative 1 times negative 1, that's positive 1. So you have minus 1 here. So negative 4 minus negative 1, that's negative 5. Are we good with this? Okay. So we have 1/2. What's the one inside? Square root of 49 plus 16 plus 25. So just simplify this and you will get the area. So 16 plus 25, that's 41. 49 plus 41, that's 90. Square root of 90 over 2. So verify. Please check my arithmetic on this part. So 16 plus 25, that's 41. 41 plus 49, that's 90. So square root of 90 over 2. And you can simplify this square root of 90 as 3 square root of 10. But this one is totally fine with me. Okay? This guy here, it's just fine. So we'll get this as our final answer. Okay? Another example here. Find the area of the triangle determined by these points. So similar solution. So again, you can work with me. So I'll be working on this slide here, and please work on your desk and let us compare answers. So I'll use again P1 as my initial point. So P1, P2, this is the vector 1 minus 2, then 1 minus 6, and then 1 minus negative 1. So 1 minus 2 here, 1 minus 6 here, 1 minus negative 1 here. And this is negative 1, negative 1, 5, and then 2. And then next, you have P1, P3. So it's 4 minus 2, 6 minus 6, 2 minus negative 1. 4 minus 2, that's 2. 6 minus 6, that's 0. And 2 minus negative 1, that's 3. Then, next step, we get the cross product. So we have here I, J, K in the first row. Second row, it's negative 1, negative 5, 2. Third row, it's 2, 0, 3. So here you got determinant negative 5, 2, 0, 3, I minus determinant negative 1, 2, 2, 3, J plus. Third, you have negative 1, negative 5, 2, 0. K. And this is negative 15 I, negative 15 I minus quantity, negative 3 minus 4 J plus 0 minus 10 or minus negative 10 K. And this is equal to the vector negative 15. Here you have positive 7. And here you have positive 10. Okay? Or do we have the same cross product? So verify and check if I made some arithmetic errors in here. But now, so if I'm going to use this, assuming that this is the correct cross product, we have now the area equals 1/2 norm P1, P2 cross P1, P3. But this is equal to 1/2 square roots of negative 15 squared plus 7 squared plus 10 squared. And this is equal to square root 15 squared. 15 squared, that's 225. Okay, 225 plus 7 squared, that's 49. And then 100 squared, that's 10 squared, that's 100. Then all over 2. And then that's C, 225 plus 49 plus 100, that's 374. So the area is square root of 374 over 2. And we can just write this as our final answer. Okay? Question? Are we good? So in the previous theorem, okay, in particularly in this theorem, we have what we call the vector triple product, and it's calculated in this way. Okay, there's another triple product that we will consider. It's called the scalar triple product. Okay, so if u, v, and w are vectors in 3 space, then u dot v cross w is called the scalar triple product of u, v, and w. Okay? Scalar triple product of u, v, and w. Okay? Now, unlike the vector triple product, this scalar triple product can be calculated easily using this formula. So u dot v cross w, it's just the determinant of the matrix with these entries. The first entry, it's the first factor in the dot product, that's u. I mean, the first row, it's the components of the first factor in the dot product u. The second row, it's for this second factor here, V. The third row, it's for your third factor here. Okay? So this scalar triple product, we can calculate this easily using this determinant. Okay? So for example, we want to find the scalar triple product of U dot V cross W. I mean, find the scalar triple product U dot V cross W of the vectors U, V, and W here. Okay? So take note, your U it's I minus 3j plus k. Your V it's equal to negative 2i plus 6k. Your W it's negative 5i minus j plus k. Look at V, there is no j, meaning the coefficient of j is equal to 0, meaning the second component of V is equal to 0. So you have to spot that. But anyway, U dot V cross W, this is the determinant of the matrix 1, negative 3, 1. And then you have negative 2, 0, 6. And then you have negative 5, negative 1, 1. So determinant of E3 by 3 matrix. And you can do this in a way you know. Okay? You can use our shortcut. You augment 2 columns here and then the sliding. So going down, going down, going down. You multiply the entries and add them, and then going up here, you multiply the entries and then subtract. Correct? So you can use that. You can also use your the cofactor expansion along any row. You can use cofactor expansion along the second column or the second row because there's a 0 here, etc. So you can use any method to get the determinant of this. Okay, but let's see. So the determinant will be, so 1 times 0 times 1, that's just 0, plus. Then here, negative 3 times negative 3 times 6 times negative 5 here. So if you write your first column here, the one at the bottom here will be negative 5. Okay, so negative 3 times 6 times negative 5, this is what? Positive 90. That's positive 90. So negative 6 times, negative 5 times 6, that's negative 30. 30 times 3 here, that's 90. Then lastly, you have 1 times negative 1 times negative 2, that's positive 2. Okay? Minus quantity. Going up, this is 0 here. And then here you have negative 1 times 6 times the 1 in here, that's your 1 there. So that's negative 6. And then here you have 1 times negative 2 times negative 3, that's positive 6. Correct? That's positive 6. So the scalar triple product, this is just 92. Okay? Question? Okay, so that's your scalar triple product. Now, for this scalar triple product, okay, we have the following nice property. So you have u dot v cross w. This was the definition that we have. This can also be calculated as w dot u cross v. And this is also equal to v dot w cross u. So how can we remember this easily? So you have your u v w. You move counterclockwise or clockwise, sorry. You move clockwise. So look at this. U dot v cross w. V dot w cross u. Look at that. V w cross u. Or w dot u cross v. W dot u cross v. Okay? So you can look at this rotation here. Okay? So you can easily remember this guy here. So that's the scalar triple product. But what is this? How is this useful to us? The absolute value of the determinant of this guy here is equal to the area of the parallelogram in the two space determined by the vectors u and v. Okay? So the absolute value of the determinant is equal to the area of the parallelogram in two space determined by the vectors u and v. Let's look at the previous formula for the area of the parallelogram. This guy here. We considered vectors in the parallelogram, vectors in the tree space. Of course, you have the cross product, which is which only works for the tree space. But in this guy here, in this theorem here, we only look at vectors in two space. And we are talking about cross product. So the question is, how are we going to determine, or how are we going to relate the cross product with this formula? Okay? So what you're going to do, so you know you are in the two space, but we have been working with cross product, which is only applicable in three space. So what we're going to do is to construct the tree space. Okay? So this is your tree space. This is your X, this is your Y, this is your Z. And then let's look at the XY plane only. Let's look at the XY plane only. Okay? On the XY plane, the third component will be 0. Okay? The third component will be 0, which means if we look at the vector u in the tree space, you can have the vector u, okay, to be the vector with components u1, u2, comma 0. Okay? And then you can have the vector b. If this is your vector b here, you can have this to be the vector with components v1, v2, 0. So now it seems that you are in the three-dimensional space, except that the third components are 0. So you are on the two-dimensional space also. You are on the XY plane. Correct? which means we can use the formula that we know. We can use the formula that we already know. Okay? So in here, what we're going to do is to consider this guy here, okay? These two vectors here. So you will have U cross V, and then you get the magnitude of this. That's the area of the parallelogram in the tree space. Okay? But this guy here, what is this? You already have this, U and V. So how do we get the cross product? So you have, let me use the determinant, I, J, K, U1, U2, 0, V1, V2, 0. Okay? And then you get the norm of this. So inside you have the determinant of the 3 by 3 matrix, and then you get the norm. Okay? But what's this? If you look at this, you can get the determinant of this matrix by using cofactor expansion along the fourth or along the third column. But what is this? This is equal to the norm, okay? This is equal to the norm of K times the determinant U1, U2. Let me adjust. So you have the determinant U1, U2, V1, V2, and then you have your K here. Take note, I'm still using the norm because K is a vector. Okay? And therefore, if we use this is a scalar, this is a vector, this becomes the absolute value of the determinant U1, U2, V1, V2, absolute value, and then the norm of K. But K is a unit vector, so this guy here, it's just 1. Which means you just have the absolute value of the determinant of the matrix U1, U2, V1, V2. Okay? So this is the proof of this theorem. Okay? Question? Now, what about the following figure? Oh, sorry. Let's look at some example in here. Okay? So we want to determine the area of the parallelogram with vertices P1, 1, 2, P2, 4, 4, P3, 7, 5, and P4, 4, 3. Okay? So in here, believe me that this is a parallelogram. Okay? Believe me that these 4 points will form parallelogram. Okay? We are just going to use 3 points because we just need to form the vectors U and V. So say you have this point here. Anyway, so let's try to draw. Since this is just into space. So you will have 1, 2, 1, 2, 3, 4, 5, 6, 7. The highest is 5, 1, 2, 3, 4, 5. So you have 7, 5. It's somewhere here. And then 4, 4. So 4 here and 4 here. 1, 2, 3, 4. 4 here. And then 4, 3. And then this guy here. 4, 3. And then, what's the other guy? 1, 2. 1 and then 2 here. 1 and 2 here. Okay? So how do we see this? So where is the parallelogram? The parallelogram will look something like this. Here, then here, then here. So that's the parallelogram. Okay? So it is not perfect, but that's the parallelogram. So let's look at the labels here. This is your P1. This guy here, it's your 4, 3. So that's your P4. This guy here, it's your 4, 4. That's your P2. And then this guy here, it's your 7, 5. That's your P3. Okay? So we can consider this vector here and then this vector here to be our U and V. Okay? So we will consider these two vectors here to be our U and V. So it means we need the vector P1, P2. So P1, P2. So 4 minus 1 there, comma 4 minus 2. And this is the vector 3, comma 2. And then the other vector that we need, it's your P1, P4. P1, P4. So P4, that's 4. So 4 minus 1, comma 3 minus 2. This is the vector 3, comma 1. Following? And therefore, the area of the parallelogram is just the absolute value of the determinant of this. So, absolute value of the determinant 3, 2, then 3, 1. This is equal to the absolute value of 3 times 1 minus 3 times 2. That's 6 here. And this is equal to absolute value of negative 3. This is 3. So that the area of this parallelogram is equal to 3. Okay? So take note that you have to place the proper what do you call this? the proper location of your vertices, and don't just use any 3 points. Okay? Because vector P1 and P2 are P1, P2, and vector P1, P4 will generate this parallelogram. If you use, however, P1, P2, and P1, P3, you will generate a different parallelogram. And you will get a different area. Okay? So you have to make sure that you use the proper um, arrangement, or the proper sides, or the proper vectors of the parallelogram. Okay? Question? Now, let us look at this. The absolute value of the determinant given by this. So determinant of U1, U2, U3, V1, V2, V3, W1, W2, W3. This is equal to the volume of the parallelepiped in the tree space determined by the vectors U, V, and W. And if you look at this is your scalar triple product. Okay? The determinant here will give you the scalar triple product. Okay, but anyway, volume of the parallelepiped in tree space. So if you have three vectors, so you will have this vector 1, vector u, vector v, then you have the vector w here. So in the three-dimensional space, you will be able to construct a parallelepiped. It's like a cube if you have the or a rectangular box, if everything are right angles. In this case here, it doesn't have the angles between two vectors may not be right angles. Okay, so what you will get is a parallelepiped. It's still like a box. Okay, so anyway, so if you have these three vectors in this formation, the parallelepiped that you will be able to construct is the following. So you will have something like this, something like this, and then you will have something like this guy here, this guy here, and here. And then this guy here, it's for this part, and then for this part, and then this guy here somewhere at the back. In fact, this guy here, it's somewhere at the back. And then also this guy here. Okay? So this is the parallelepiped that you will be able to construct. Okay? So you will get something like a rectangular box. So let me just fix this. And then this guy here, as I have said, this is somewhere at the back. Okay? And the vector v is also somewhere in the back. So you will get something like a box. So this is a parallelepiped. Okay? You want to get the volume of this, all you need to do is to get the determinant of this guy here. And you get the absolute value, by the way. Because determinant can be negative. But since you are talking about the volume, it has to be positive, so you have to get the absolute value. Okay? So if you need to get the proof for this formula, it's similar to what we did in the area of rectangular area of a parallelogram, but this time you will now consider the height here. So area of the base, this is just is a parallelogram, so you can calculate that easily using the formula before, but this time you will get a height. Okay, you'll get a height in here, and to get the height from this to that part, you do the same, you'll do similar computation as in the one that we did in the parallelogram formula, area of the parallelogram formula. Okay, so that's how we're going to, that's how you're going to derive this formula here. Okay, but anyway, let us apply this formula to the following example. Determine the volume of the parallelepiped determined by these vectors here, u, v, and w. Okay. So first is you just need to get the determinant of the matrix whose entries are given by these vectors. So you have 2, -6, 2, 0, 4, -2, and then 2, 2, -4. Okay. So in here, let's use cofactor expansion. Let's just use cofactor expansion just to have some practice on that. So -1 raised to 1 plus 1. So I'm doing cofactor expansion along the first column. -1 raised to 1 plus 1 to absolute value. Determinant, I mean, for -2 to -4. And then this guy here is 0. And then for this guy, you have plus -1 raised to 3 plus 1. Okay. Times 2. Determinant of -6 to for -2. Okay. Then let's compute. This is equal to 2 times 4 times -4. You have -16 minus 2 times -2. That's -4. Plus you have here 2 times -6 times -2. That's 12 minus 4 times 2. That's 8. And this is equal to, you have -16 plus 4, that's -12 times 2, that's -24. Here you have 12 minus 8, that's 4 times 2, so plus 8. So this is equal to -16. That's the determinant. And now we need to get the absolute value to get the volume. So therefore, volume equals the absolute value of -16. This is equal to 16. Yes, question?
Yeah, aren't we missing the one of the coefficients? Because I see the one for 2. I see another one for 2, but I don't see the one for 6.
No, I am expanding along this column.
Oh, okay. Sorry.
Yeah. Oh yeah, that's a good observation. So one would think that I did this one here because they're both 2. Here 2 and 2 also. But yeah, I'm doing the expansion along the first column. Okay, other questions? Okay, so let's now look at this. So if vectors u, v, and w have same initial point and they lie in the same plane, sorry, suppose u, v, and w have same initial point, then they lie in the same plane if and only if the scalar triple product is equal to 0. Okay? So, you have three vectors, u, v, and w. Okay? Then you calculate the scalar triple product. And if it happened that it's equal to 0, then u, v, and w are on the same plane. Okay? And of course, if you have three vectors lying on the same plane, then the scalar triple product will be equal to 0. How is that? Let's go back to this. Look, if you have the three vectors, u, v, and w, there's a possibility that you can construct the parallelepiped, meaning you will be able to get this three-dimensional object. Correct? But what if you were not able to construct the three-dimensional object because the three vectors are on the same plane? It only means that there will be no height for your parallelepiped, because in fact you just have a flat surface. There is no height, and therefore the volume will be 0 because height is equal to 0. Correct? So if you have three vectors and all of these vectors here lie on the same plane, then this determinant here will be equal to 0. Volume will be equal to 0. Okay? And similarly, if you have some object and you look at the volume and found out that the volume is equal to 0, okay? And by volume, I mean it in quote unquote, okay? Quote unquote volume is equal to 0. It means that you don't have a three-dimensional object, correct? So that's what this theorem is saying. You got three vectors, okay? If the scalar triple product is equal to 0, then the three vectors are on the same plane. Conversely, if these three vectors are on the same plane, then you don't have a three-dimensional object and the volume will be equal to 0, which means the scalar triple product will be equal to 0. Okay? Now, being on the same plane also means that they are coplanar. So just a term. Determine whether the vectors u, v, and w are coplanar. Okay? So all we need to do here is just to get this scalar triple product and show that it's equal to 0. If it is not equal to 0, then they are not coplanar. They don't lie on the same plane. If the determinant is equal to 0, then they lie on the same plane. Okay? So let's see. U dot v cross w here. So we look at the determinant, negative 2, 1, 0, 0, negative 1, 1, negative 4, 1, 1. Okay? And then let's use the other technique that we know in solving determinant of 3 by 3 matrices. So in here, let me rewrite this guy here. You have negative 2, 1, 0, 0, negative 1, 1, negative 4, 1, 1, and then we augment the first two columns, negative 2, 0, negative 4, 1, negative 1, 1. So for this guy here, we multiply this guy also and this guy here. So you have negative 2, negative 1, 1. So that's positive 2. 1, 1, negative 4. That's negative 4. And of course, this is 0. And then for this guy here, this guy here, and this guy here. So of course, this guy here, it's just 0. This guy here, 1 times 1 times negative 2, that's negative 2. Then here, 1 times 0 times 1, that's just 0. So meaning this determinant here, it's 2 minus 4 minus, you just have negative 2 here. And indeed, this is equal to 0. So negative 2, so 2 minus 4, that's negative 2, minus negative 2, that's equal to 0. So therefore, U, V, and W are coplanar. Therefore, U, V, and W are coplanar. Okay? Question? Question here. Okay. Now, let's look at some more geometric applications of what we've learned so far. Suppose we have two non-intersecting and non-parallel lines in R3. Then these lines here are called skew lines. So two non-intersecting, non-parallel lines in R3. Okay? Remember, in R2, if you have two parallel lines, okay, if you have two parallel lines, then they will not intersect in the two-dimensional Cartesian plane. You have two parallel lines, they will not intersect. So in R2, you have this line here, you have this line here, parallel. It means that they will not intersect. Non-intersecting. Okay? Also in R2, suppose you have two lines that are not parallel, okay? Definitely they will intersect. Non-parallel, they are intersecting. So these are the two cases in the two-dimensional Cartesian plane. In R3, it is possible that lines are not intersecting and also not parallel. Okay? For those pair of lines, we call them skew lines. Think of this as the the edge of your box. Okay, let's look at this. So say you have a box in here. Okay, say you have a box in here. Okay, if you consider this part here, this edge here, okay, and this edge here, okay, if you extend this edge here indefinitely, it will not intersect this edge here. Can you imagine that? Even if you extend this edge here indefinitely, they will not intersect. And notice they are not parallel because here, this is going down and up. Okay, here you are, this is going left and right. So they are not parallel. This guy here, it's parallel to this. They will not intersect, but they are parallel. This guy here is also parallel with this. They will not intersect, and they are parallel. Now, this guy here, it's parallel to this edge. Okay? It's also parallel to this edge here and this edge here. They are parallel, they will not intersect. Okay? But for this pair and this pair, they are non-intersecting, also non-parallel. So these two pairs here, they are called skew lines. So there's a possibility that you will have lines that are not intersecting and not parallel in the three-dimensional space. Okay? So if you are asked to determine whether two lines in R3 are skew lines, you have to check two things: non-intersecting and non-parallel. So for example, determine whether these two lines here are skew lines. Okay, determine whether these two lines here are skew lines. So if you look at L1, let's write L1 and L2 in the parametric equations form. Your L1, you have your x equals 1 minus 2t, 1 minus 2t, y equals 2 minus t, z equals 3 plus 3t, 3 plus 3t. This is your L1. Your L2, you have your x equals 4 plus 3s, y equals negative 1 minus s, sorry, negative 1 plus s, z equals 2 plus s. Okay? So we want to show that these two lines here are skew lines or not. And in order to do that, we have to show whether L1 and L2 are parallel. Okay? And whether L1 and L2 are intersecting. For parallelism, it is easy because L1, you have these parametric equations, and you just look at the coefficients of your parameter t. Those are the components of the vector for which your L1 is parallel to. Okay? So from here, L1 is parallel to the vector minus 2, minus 1, 3. Your L2 is parallel to the vector, the coefficients of S here, 3, 1, 1. 3, 1, 1. Let me label this as your V1 in here, this guy here as your V2. So if L1 is parallel to V1 and L2 is parallel to V2, in order to determine whether L1 and L2 are parallel, we have to determine whether V1 and V2 are parallel. Okay? So in here is V1 parallel to V2, meaning can we find a scalar? Can we find a scalar K such that V1 equals K V2? So find scalar K such that V1 equals K V2. If there's none, therefore they are not parallel. And therefore these two lines here are not parallel. But what does this mean? You have negative 2, comma negative 1, comma 3. So you will have this equals K times the vector 3, 1, 1, 3, 1, 1. Or that we have um, negative 2 equals 3K, negative 1 equals K, 3 equals K. And this guy here implies some contradiction. Okay, so this guy here cannot happen. K equals negative 1 equals 3, and this is not correct. So contradiction. Contradiction. Which means V1 and V2 are not parallel, and so L1 and L2 are not parallel. So let's just write this. So L1 and L2 are not parallel. Okay? Yes, question?
Yes. So basically, if we would do this step and we wouldn't find any contradiction, that would mean they are parallel, right?
Yes. Yes.
Okay.
If you were able to find that scalar K satisfying something like this, then the two lines are parallel.
All right.
If
Makes
you
sense.
cannot find, yep, if you cannot find that K just like this, it's a contradiction now, then they are not parallel. So that's the first one, non-parallel. So we are sure now L1 and L2 are not parallel to each other. For the non-intersecting, okay, this will need some work. Okay, to do this, let's look at this. Let's copy this guy here. Okay, to show that they do not intersect, we need we try to find, actually we should not be able to find values of t and s that will make them equal. Okay, or um, equivalently, if we were able to find some values of t and s so that the corresponding x, y, z for L1 and L2 are the same, then L1 and L2 are intersecting. Okay? So how do we solve this? We need to solve this guy here. So we need to solve the following system. 1 minus 2t. 1 minus 2t, this is the x for L1. Okay, that's the x for L1. And we want, or we don't want that to be equal to the x for the L2. Okay? We may want or may not want it. But anyway, we just equate them. x1, the x in here equals the x in here. So 1 minus 2t equals 4 plus 3s. And then also, we equate the y's. 2 minus t. This is equal to minus 1 plus s. And also, we equate the z. Okay? 3 plus 3t equals 2 plus s. So we don't want to find the solution, meaning this system must not have a solution in order to conclude that L1 and L2 are not intersecting. Okay? So these three equations here tells us that their corresponding coordinates, x here equal, y here equal, z here equal. Okay? But we don't want that to happen. We don't want all the coordinates to be equal correspondingly. We don't want our x to be equal to z. We don't want our x to be equal to x here when y's and z's are equal. Okay? Or if the x's are equal and the z's are equal, we don't want our y to be equal. Or if x's are equal, y's are equal, we don't want our z's to be equal. Okay? Because in those cases, we will get non-intersecting lines. So, we want this to have no solution, in short. But let's see. For this guy here, let's look at this. We can have our S. So let us label this. Let us label these equations here. Equation 1, 2, and 3. Equation 1, equation 2, equation 3. From equation 2, let's write S in terms of T. Our S will be, so this guy here, we put this on the other side. So our S will be 3 minus T. Okay? And then we plug in this S to equation 3. So plug in 3. We will get 3 plus 3t equals 2 plus s, but s is 3 minus t. So we solve this. What do we get? This guy here on the left hand side, this is 5 minus t, which gives us what? 3t. We put the t on this, we'll have 4t equals. Then we put the 3 on the other side, you have 5 minus 3, which is equal to 2. This gives us t equals 1/2. Okay, following. If t equals 1/2, we solve for s. So, s, this is equal to 3 minus t, which is 1/2. So what is this? 5/2. S equals 5/2. So we have a value for s. We also have a value for t. What we're going to do is to verify that this s and t will solve this system. Now, we already used equations 2 and 3. So let's use equation 1 to verify whether s and t will solve it. Okay? So let's see if it will solve it. you have plug in t equals 1 half and s equals 5 halves in equation 1. We have 1 minus 2 times 1 half. Is this equal to 4 plus 3 times 5 halves? Well, on the first here, 2 times 1 half, that's 1. 1 minus 1. And then in here, 4 plus 15 halves. And here, left-hand side, this is equal to 0. And definitely, this is not equal to 4 plus 15 halves. So this guy here is not a solution. And there are no other possible solutions. Because these values, t and s, will solve equations 2 and 3 as a system. But does not solve the complete system here, meaning um, including equation 1. So here, this system does not have a solution. So let's label this system as a star. Let's just label this as a star. The system star does not have a solution. So L1 and L2 are non-intersecting. Are non-intersecting. And that's it. You showed that they are non-parallel, and now they are non-intersecting. We therefore conclude that L1 and L2 are skew lines. Okay? So again, two things that you need to show. If you want to show that lines are skew lines, they must not be parallel and they must not be intersecting. For parallelism, all you need to do is to check whether the vectors to which each line is parallel to, okay, are parallel or not. And then for intersections, you need to solve this system. Okay? For this example, let L1 be the line parallel to 162 and contains the point 110. And L2 be the line containing negative 152 and 1, negative 1, negative 6. Show that L1 and L2 are skew lines. And then we want to find their distance. Because if they are skew lines, they are non-parallel or non-intersecting. You can find distance between these two lines. Okay? Let's see. For L1, let us transform this information into parametric equations. So you have your x equals 1, because it contains the point here, 1 plus t. For y, we have here 1 plus 60. 1 plus 60. For z, you have 0 plus 2t. Z 0 plus 2t. So let me just write this as 2t. Okay? This means that your L1 is parallel to the vector 1, 6, 2. And let me label this as your V1. For L2, we are given 2 points, but we can get the difference between these 2 points to get the vector. Okay? And then we use one of the points for this part here. So you have your x equals. Let's use this point here, negative 1, 5, 2 as our point. So negative 1 plus, and then the vector will be 1 minus negative 1, 1 minus negative 1 s. Y, it's 5 plus negative 1 minus 5. So negative 1 minus 5 s. And your z, this is 2 plus quantity negative 6 minus 2 s. Or simply, this is negative 1 plus 2s. This guy here, it's 5 minus 6s. And this guy here, it's 2 minus 8s. And this also tells us that L2 is parallel to the vector 2, negative 6, negative 8. And let's label this as your V2. Okay? So we want to show they are skew lines. Okay? So to show V1 and V2 are non-parallel. So step 1, V1 not parallel to V2. Okay? So let's see. Let's have V2 equals KV1. This implies that, so your V2 it's 2 equals K times 1. And then you have negative 6 equals 6K. And then negative 8 equals 2K. So 2 equals K. So this 2 equals K times 1. The negative 6 equals 6 times K. The negative 8 equals 2K. But this guy here implies K equals negative 1. This guy here also implies K equals negative 4. So you got 3 different values of K. So this is not possible. Okay? So this implies no scalar K exists. No scalar K such that, let's write that, such that V2 equals KV1 exists. So V1 and V2 are not parallel. So V1 and V2 are not parallel, which means the two lines are not parallel. Okay? So this means L1 and L2 are not parallel. Okay? Question so far? Now, for the non-intersecting, let's look at this. Step 2, non-intersecting. So how do we do this? We compare again coefficients. We compare again coordinates. So x equals this x, y equals this y, z equals this z. And we show that there's no solution to the system. Okay? So for the first one, 1 plus t equals minus 1 plus 2s. So minus 1 plus 2s. For the second one, you have 1 plus 6t equals 5 minus 6s. And finally, for the third one, we have 2t equals 2 minus 8s. 2t equals 2 minus 8s. Okay? So we want to solve for this system. Let us label this equation 1, equation 2, equation 3. And then let's use equation 3. We write t in terms of the s. So from 3, t is simply, so we divide everything by 2. We have 1 minus 4s. Okay? Then let's substitute this t in equation 1. So substitute in equation 1. We will have 1 plus t. So 1 plus 1 minus 4s. This is equal to minus 1 plus 2s. So this is just 2 minus 4s equals minus 1 plus 2s. And we will get 3. So we put this negative 1 to this side. So 2 plus 1, that's 3. And then we put minus 4s to the other side. Will give us 4 plus 2s, which is 6s. And this gives us s equals 1/2. Which means if we plug this in, so substitute in this part here. So when s equals 1/2, you have t equals 1 minus 4 times 1/2. 4 times 1/2, that's 2. So 1 minus 2, that's negative 1. So we have the t, we have the s. We used equations 3 and 1. So we plug in equation 2. Okay? In equation 2, we now have 1 plus 6 times t. T is negative 1. Is this equal to 5 minus 6? S is 1/2. On the left-hand side, we have 1 minus 6. So that's minus 5. On the other side, you have 5 minus 6 times 1/2. That's 3. So negative 5, this is not equal to positive 2. So this system has no solution, and therefore L1 and 2 are not intersecting. So this gives us star has no solution. This tells us L1 and L2 are non-intersecting. Okay? Question? Okay. For the last part, find their distance. Find their distance. Now, in order to find the distance of two skew lines, okay, what we're going to do is to find a plane that will contain one of the lines and is parallel to the other line. So look at this. Let us look at that box that we saw here. So these two guys here are skew lines. Okay. Of course, the distance, we know that it's the shortest distance of the shortest distance possible from a point, okay, from necessary point on one line to the necessary point on the other line. So there's the shortest distance possible, okay? So for example, if you extended this guy here, so if you extended this towards this direction, okay, towards this direction and towards this direction up there, and then you extended this line here, okay? So you get point here, you get point here, you get the distance there, okay? Say d sub 1. You also get this point here to this point here, you get your d sub 2. But there's also a possibility where you get this point here and you get some point here. This is your distance 3, and etc. So you collect all possible pairing of one point on the line in this vertical line here and at another point on this line here. You get all possible pairings. You get the distance between those pairs. And you find the shortest distance. That will be called the distance between skew lines. Okay? So that's the illustration. Let's go back to this. And so what do we really need here? The distance between L1 and L2, this is the smallest, so the minimum of all possible distances, point 1, point 2, okay, where point 1 is a point in L1, is a point on L1, and point 2 is a point on L2. So that's how we define distance between two lines. And this also works in the distance between skew lines. Okay? You get all possible distances and you choose the smallest. That will be the distance between the two lines. But there is an easier way. For skew lines, there's a very a good way to determine the distance. Okay? If we look at this again, what you can do is to get this plane containing this line here. Okay? And therefore, if this plane here is parallel to this line, then all possible the distance between this line and this plane will be the distance of this line and this line here. Okay, let's go back and let's try to draw that again. So you have two skew line. You have you have a pair of lines which are skew. So you have this line here, and then maybe another line somewhere here. And this is skew line. You are in the three-dimensional, space, so L2 and L1. So what we're going to do is to get the plane containing L1. Let's label this as pi. The plane containing L1 but not L2. That's the first step. The second step is to find the distance. Okay, so find a plane, containing one of the lines, okay? And then the step 2, you find the distance of that line, of that plane from the other line. So find the distance between the plane and the other line. Okay, so this is what we're going to do in order to find the distance between two skew lines. So the question is, let me complete this statement here. Find the plane containing one of the lines and is parallel to the other line. Of course, there will be infinitely many planes containing this line L1 here. There are infinitely many of them. But there's only one plane which will contain this line L1 and is parallel to line 2. That's what we need. Okay? So we need to find that plane. In order to do that, we need a normal vector. Correct? We need a normal vector to the plane. And we need a point on line L1. Okay? This normal vector to the plane can be calculated using the vector where L1 is parallel to and the vector where L2 is parallel to. Okay? So let's do that. So to find the plane, we need a normal vector. We need a normal vector. oops, this normal vector, okay, is obtained by getting the cross product of the vector v1 and the vector v2. Okay? Let's look at that, or let's look at those vectors. Where is that? So in here, this is your v1, this is your v2. Okay? So let me copy this. So we put it here. L1 is parallel to V1 and L2 is parallel to V2. Let's label the normal vector n. So we need a normal vector n. This normal vector n, and this is equal to V1 cross V2. Okay? Remember, if if the vectors are perpendicular, so we need the vector n here. If the vectors are perpendicular, then their dot product is equal to 0. Correct? If two vectors are perpendicular, then their dot product is equal to 0. So why are we taking the cross product V1 and V2? If we go back to this property here, okay, U cross V is equal to 0. U cross V is orthogonal to U. V dot U cross V is also equal to 0. U cross V is orthogonal to V. So how does that help us? If we get the cross product here, then this vector n will be orthogonal to V1. Correct? And therefore, the plane with normal vector n will be parallel to V1 or to L1. Similarly, this vector n will be orthogonal to V2, which means the plane here will be parallel to L2. Okay? Now, if we use a point on L1 to obtain the equation for the plane pi, then the plane will contain L1, okay, but not L2. So the cross product here is the one we needed in order to get the normal vector for the plane. Okay? But let's solve for the cross product to finish up the solution here. So cross product, you have I, J, K, V1 it's 1, 6, 2. V2 it's 2, negative 8, or negative 6, negative 8. So in here, we have quantity 6 times negative 8, that's negative 48 minus negative 2, or negative 6 times 2, that's negative 12. I minus, for the j, you have 1 times negative 8, that's negative 8. 2 times 2, that's 4, so minus 4. J, and then for the k, we have 1 times negative 6, that's negative 6, minus 2 times 6, that's 12, k. And this is equal to what? Minus 48 plus 12, that's minus 36, comma. Minus 8 minus 4, that's minus 12. There's a minus here, so plus 12, comma. Minus 6 minus 12, that's minus 18. So you have minus 18 here. So this vector n will be the normal vector for our pi, for our plane pi. Now we use a point on L so that the plane will contain the line L. And we use this guy here. So the equation of the plane, or an equation for the plane, an equation for the plane is given by, so remember how to write, you still remember how to write equation of the plane? So you have negative 36 times x minus the x coordinate of the point. We are going to use this. So x minus 1. Then here you have plus 12. Y minus 1. And then here you have minus 18. Z minus 0. And then you have equal to 0. So this is the equation of the plane pi. Okay? This is the equation of the plane pi. Now you have the plane pi. The last thing to do now is to get the distance of the plane pi with L2. Distance of the plane pi from L2, or vice versa. Distance of L2 from plane pi. Okay? So let me label this as your pi. Okay? And to get the distance of one line to a plane, we can just use a point on the line and get its distance from the plane. Okay? So this is our plane pi. So this guy here contains L1, contains L1, and not L2, and not L2. Also parallel to L2. Parallel to L2. Sorry, contains L1 and not L2. Contains L1 and not L2, parallel to L2. Therefore, distance of L1 and L2, this is just the distance of L2 or pi in L2 and L2. But we just need a point from L2. We are given 2 points here. So let's just use one of them. So this is just equal to the distance of pi from the point. Say, let's use this, -1, 5, 2. Well, I'll just use this 1, -1, -6. 1, -1, -6. And the formula, this is just the absolute value of what? Minus 36 times 1 minus 1 plus 12 times -1 minus 1 minus 18 times -6. So you have the absolute value divided by the square root of -36 squared plus 12 squared plus minus 18 squared. Then just calculate, and that will be the distance of the two lines. Yes, question?
Where and the first term where it's 30 minus 36, it is 1 minus 1, it is actually 0.
Yes, that's good. So this guy here is 0. This guy here, you have 12 times -2. Okay? So absolute value, 12 times -2, that's -24. Then here, minus, but there's negative here, so you just do the addition. So 18 times 6, what is this? So 18 times 6, that's 108. So for the numerator, we'll get 84 there. Okay. For the denominator, we have the square root of 36 squared. We have 1,296 plus 12 squared, that's 144 plus 18 squared, we have 324. So plus 324. So for the denominator, you have 1296 plus 144 plus 324, that's 1,764. And you get the square root of this. I think we can get the square root of that. Okay. What's the square root of that? It's 42. So in here, you will have, in the numerator, you will have 84. In the denominator, you have 42. 84 divided by 42, this is just 2.